Some projects on Earth are so massive, they once sounded completely impossible, too expensive, too dangerous, and built in places where construction should never work: deep oceans, burning deserts, frozen mountains, and unstable ground. For years, many experts believed these projects could never be completed. But human ambition is powerful. With bold ideas, advanced technology, and thousands of engineers working together, these impossible visions slowly became reality. Today, across our planet, enormous bridges stretch across oceans. Tunnels run deep beneath mountains and seas. Giant dams control the power of entire rivers. And futuristic cities rise where empty land once existed. These are not just buildings or infrastructure. They are some of the most astonishing mega-projects ever created, projects that pushed engineering to its absolute limits. In this video, we explore the incredible stories behind the world's most massive construction achievements. The moments when humans refused to accept impossible and built the unimaginable. There is a point, approximately halfway across the Lake Pontchartrain Causeway in Louisiana, where land disappears entirely, not fades, not recedes into the distance, disappears. In both directions, behind you and ahead of you, the bridge extends to a horizon line beyond which there is nothing but sky and water. The road continues, obviously, because you are on it, and it continues in both directions, obviously, because you arrived from somewhere and are going somewhere. But the visual evidence for these propositions is entirely absent. You are, by every available sensory measure, in the middle of a lake, on a road, surrounded by water, with no land in sight. The Lake Pontchartrain Causeway consists of two parallel bridges spanning approximately 24 miles across the lake that separates the New Orleans metropolitan area from the North Shore communities. The first span opened in 1956, at the time, the longest bridge over water in the world. The second, parallel span, opened in 1969. Together, they carry approximately 40,000 vehicles per day, making them among the most heavily used long-distance water bridges in the United States. Guinness World Records recognized the Causeway as the longest continuous bridge over water in 2011, though this designation has been subject to definitional debate based on how continuous and over water are operationalized. The structural system is deliberate in its simplicity: precast concrete sections resting on concrete piers extending in a straight line across the lake without curves or significant grade changes. The design was chosen for durability and ease of maintenance. The brackish water of Lake Pontchartrain is aggressive to concrete and steel, and the straightforward structural approach minimizes the number of maintenance-intensive connection points. The bridge crosses the lake at a height of approximately 16 feet above the water surface, not high by bridge standards, but sufficient for the recreational watercraft that use the lake. Hurricane Katrina, in August 2005, tested the causeway in ways that its designers had not fully anticipated. Storm surge and wave action damaged sections of the bridge, a reminder that a 24-mile structure in a hurricane-prone coastal environment is not simply an engineering problem, but a meteorological one. The causeway survived, largely intact, while much of the surrounding infrastructure was catastrophically damaged. Repairs were completed and the structure returned to service, but the event established that the lake it crosses is not the benign body of water that its normally still, brown surface suggests. Under the right meteorological conditions, Lake Pontchartrain can become, briefly, something more demanding. Bosco Verticale, Italy, in the concrete jungle of Milan, two towers rise like living, breathing organisms. This is Bosco Verticale, the vertical forest. It is a radical departure from the steel and glass boxes that dominate modern cities. These two residential towers, standing 360 and 250 feet tall, are home to 900 trees, 5,000 shrubs, and 11,000 floral plants. If you laid all this vegetation flat, it would cover an area equal to 2 hectares of forest. This isn't just landscaping, it is a biological shield, a microclimate creator, and a bold solution to urban pollution. The engineering challenge here was not just structural, but botanical. Architects and botanists worked together for years to select the right trees, oaks, beeches, and larches that could survive the wind and altitude. These trees had to be pre-cultivated to acclimate them to the conditions. The balconies are reinforced with steel and concrete to support the immense weight of the soil and water. Speaking of water, a sophisticated automated irrigation system uses recycled greywater from the building to keep the forest thirsty, ensuring sustainability. The trees are anchored with safety cages to prevent them from falling during storms, tested in wind tunnels to withstand gusts of up to 120 mph. Living here means living inside a canopy. The leaves filter sunlight, creating a natural temperature regulation system that reduces the need for air conditioning in summer and heating in winter. They absorb carbon dioxide and dust particles, producing oxygen and purifying the air for residents. The towers have become a thriving ecosystem for birds and insects, bringing biodiversity back to the city center. The facade changes with the seasons, green in summer, red and orange in autumn, and bare yet sculptural in winter. Bosco Verticale has won awards worldwide, inspiring similar projects from China to the Netherlands. It challenges the idea that nature and urbanization must be enemies. It proves that we can densify our cities without losing our connection to the earth. It is a prototype for the city of the future, one where architecture doesn't just house humans, but heals the environment. Rain Vortex, Singapore airports are usually stressful places of lines and luggage, but Changi Airport in Singapore is a destination in itself, thanks to the Jewel. At the center of this glass-domed lifestyle hub falls the HSBC Rain Vortex, the world's tallest indoor waterfall. Water cascades 130 feet down from an oculus in the roof, plunging 7 stories into the basement forest below. It is a mesmerizing column of water surrounded by the Shiseido Forest Valley, a terraced indoor garden with 2,000 trees and 100,000 shrubs. It brings the awe of the rainforest into the comfort of air conditioning. The engineering behind this liquid sculpture is smart. The roof is a toroidal glass grid that supports the weight of the water mechanism. The waterfall flows at a rate of 10,000 gallons per minute during peak shows. But where does the water come from? It's recirculated rain. The roof is designed to funnel rainwater into the vortex, reusing Singapore's frequent tropical downpours. This water helps cool the interior, reducing the load on air conditioning systems, and is used to irrigate the surrounding plants. The water falls through an acrylic funnel at the bottom that prevents splashing, keeping the visitors dry. At night, the rain vortex transforms. Hidden projectors beam light and images onto the falling water, turning the cascade into a 360-degree screen for a sound and light show. Music swells and the water dances with color. It creates a hypnotic atmosphere that makes travelers forget they are in transit. The Jewel and its rain vortex redefine what public infrastructure can be. It turns an airport terminal into a Garden of Eden. It creates a sense of place and wonder, welcoming visitors to the Garden City before they even step outside. It is a masterpiece of biophilic design, soothing the weary traveler with the sound of falling water. Emosson Dam, Switzerland. High in the Swiss Alps, near the border with France, lies a concrete beast holding back the weight of a melted glacier. The Emosson Dam is a monumental arch dam standing 591 feet tall, a curved shield against the immense pressure of millions of tons of water. It is situated in a rugged, breathtaking landscape at an altitude of over 6,300 feet, where the air is thin and the weather is unforgiving. This isn't just a wall, it is the heart of a complex hydroelectric system that powers the region with clean, renewable energy. The reservoir behind it, the Lac d'Emosson, holds 227 million cubic meters of water, turning the valley into a deep blue battery for Europe. Constructing this titan required a logistical miracle. Between 1969 and 1975, workers battled snow, avalanches, and extreme cold to pour the concrete. There were no highways here. Materials had to be transported via cable cars and helicopters. The dam's double curvature design is an engineering classic, directing the force of the water into the solid rock of the canyon walls. It creates a seamless bond between man-made structure and natural geology. But the engineering didn't stop there. Deep inside the mountain, invisible to the naked eye, is a labyrinth of tunnels and power stations. The Nanpu Bridge pumped storage plant, located nearby, uses this reservoir to store excess energy, pumping water up when demand is low and releasing it when demand peaks. The visual impact of Emosson is staggering. From the top of the dam, you look down a sheer drop on one side and across a vast, mirror-like lake on the other, reflecting the snowy peaks of the Mont Blanc Massif. It draws hikers and tourists who walk across its crest, feeling the slight vibration of the water's power beneath their feet. In the summer, dinosaur tracks can be found in the nearby rocks, a reminder of the ancient history of this landscape before the ice took over. This dam represents the Swiss mastery of their environment. They have turned their mountains into power plants without destroying their beauty. It is a symbol of resilience and foresight, ensuring energy security while managing flood risks for the valleys below. The Emosson Dam stands silent and strong, a guardian of the Alps and a powerhouse for the people. On November 7, 1940, 4 months and 7 days after the first Tacoma narrow suspension bridge opened across the Puget Sound in Washington state, a photographer named Barney Elliott set up his 16-movie camera and filmed one of the most important engineering failures ever recorded. The footage, available online and viewed by every engineering student who has encountered it since, shows a suspension bridge oscillating. At first, the movement appears almost gentle, a slight undulation in the deck, a gentle, rhythmic rise and fall, and then the motion changes character. The deck begins to twist, not just move up and down, but rotate along its longitudinal axis, the two edges rising and falling in opposite directions, the tarmac surface visible at wild angles as the twisting increases. The bridge is tearing itself apart. And then, in a visual event that still seems impossible even in 2024, the center span collapses and 2,800 feet of suspension bridge falls into the Narrows. No human died in the collapse of the original Tacoma Narrows Bridge. One dog trapped in an abandoned car did not survive, but the collapse killed something else, a set of assumptions about aerodynamics, structural resonance, and suspension bridge design that had persisted, largely unexamined, since the beginning of modern bridge engineering. The first Narrows Bridge was designed with a solid deck plate, a flat, solid roadway surface that acted in the 40 mph winds that struck the bridge that morning, like an airfall. The wind did not simply push the bridge sideways. It interacted with the aerodynamics of the deck to create a resonant oscillation, the same phenomenon that can shatter a wine glass with a precisely tuned sound frequency that fed itself with increasing amplitude until the structure could no longer contain it. The replacement bridge, opened in 1950, incorporated the lessons: deeper stiffening girders, open truss side panels to allow wind to pass through the deck rather than interact with it as a solid surface, and the first systematic application of wind tunnel testing to bridge design in the United States. The current crossing consists of 2 parallel spans, the 1950 replacement and a second span added in 2007, carrying Interstate 16 across the Narrows at a height sufficient for naval vessels to transit underneath. The structure is robust. The engineering is conservative. The design incorporates, at every point, the specific humility of engineers who know exactly what happens when a bridge is not designed to respect the wind. Crossing the modern Tacoma Narrows Bridge requires knowing its history. Not because the current structure is dangerous, it isn't, beyond the ordinary risks of freeway driving, but because knowing what stood on this exact site, knowing what the Puget Sound wind did to it. Knowing that a filmmaker watched it destroy itself over the course of a few hours. One November morning turns a routine highway crossing into a continuous low-frequency meditation on the relationship between human confidence and natural forces. The water below is the same water. The wind is the same wind. Only the bridge has changed. Panama Canal, Panama. It is the path between the seas, a water bridge that severed a continent to unite the world. The Panama Canal is one of the greatest engineering achievements in human history. Stretching 51 miles across the Isthmus of Panama, it connects the Atlantic and Pacific Oceans, saving ships a treacherous 8,000-mile journey around the tip of South America. Since its completion in 1914 and its massive expansion in 2016, it has been the artery of global trade, handling huge vessels carrying everything from electronics to grain. The original French attempt in the 1880s failed due to disease and poor planning. The Americans took over in 1904, launching a war against malaria and yellow fever while blasting through the Culebra Cut, the Continental Divide. They removed enough earth to bury Manhattan 12 feet deep. The genius of the canal lies in its lock system. It doesn't use seawater directly. Instead, it lifts ships 85 feet above sea level to Gatun Lake, a massive artificial reservoir. Gravity then feeds fresh water into the locks to raise and lower the ships. It is a water elevator powered by rain. In 2016, the canal was expanded with a third lane of locks to accommodate Neo-Panamax ships, which are longer and wider than the Titanic. These new locks use water-saving basins that recycle 60% of the water used for each transit, a crucial innovation for sustainability. Electric mules, locomotives, guide the ships through the narrow chambers with inches to spare, preventing collisions with the concrete walls. The Panama Canal is more than a ditch. It is a global shortcut that dictates the design of the world's ships and ports. It operates 24/7, a silent giant facilitating the movement of the modern economy. It is a testament to human persistence, a scar on the earth that healed the divide between East and West. It remains a vital, throbbing link in the chain of civilization. Dubai Frame, UAE. It is the world's biggest picture frame, a golden rectangle rising from Zabil Park. The Dubai Frame is a metaphorical bridge connecting the city's past with its present. Standing 492 feet tall and 305 feet wide, it is positioned perfectly so that if you look through it one way, you see the historic district of Deira and the creek, the roots of Dubai. Look through the other way, and you see the glittering skyline of the Burj Khalifa and downtown, the ambitious future. It creates a literal snapshot of the city's evolution. The structure consists of two vertical towers connected by a 305-foot sky bridge at the top. The exterior is clad in gold-colored stainless steel, patterned with circles inspired by the logo of the Expo 2020. The construction utilized self-climbing formwork to build the towers rapidly, but the real thrill is inside. The Sky Bridge features a 25-square-meter glass floor panel. As you walk on it, the glass switches from opaque to clear, suddenly revealing the sheer drop beneath your feet. It is a heart-stopping moment that walks the line between terror and wonder. Inside the ground floor museum, immersive exhibits use holograms and mist to tell the story of Dubai's transformation from a fishing village. At the top, you get the panoramic view. On the way down, a future Dubai gallery uses virtual reality to predict what the city will look like in 50 years. Flying taxis, underwater colonies, and space missions. The Dubai frame faced controversy over its design origins, but it has become a beloved icon. It is a monument that frames the sky, celebrating the duality of a city that honors its heritage while racing towards tomorrow. It proves that architecture can be symbolic, functional, and deeply experiential all at once. Sunshine Skyway Bridge, Florida, USA. On May 9, 1980, in the dark and the rain and the fog of a severe storm over Tampa Bay, the MV Summit Venture, a freighter navigating by radar because visibility was near zero, struck a support column of the original Sunshine Skyway Bridge. The collision removed a 1,200-foot section of the bridge deck in seconds. 35 people died, 23 in a Greyhound bus, a pickup truck, a car, and a number of other vehicles that were on the bridge when the section collapsed, falling 150 feet into Tampa Bay before the drivers had any possibility of knowing what was happening. The current Sunshine Skyway Bridge, opened in 1987, was built to replace the original structure and to address, directly, the specific failure mode that the 1980 disaster exposed. Its two cable-stayed towers rise 430 feet above the water. The main span provides 192 feet of vertical clearance for maritime traffic, 30 feet more than the original. Massive concrete dolphins, protective islands surrounding the base of each tower, were designed specifically to absorb the kinetic energy of a vessel collision without transferring it to the tower itself. The protection system was tested in scale model simulations against the worst collision scenarios that engineers could construct. It was not built in hope. It was built in the specific and detailed understanding of what happens when a bridge and a ship meet in conditions of zero visibility. Driving the current Sunshine Skyway is, by ordinary driving standards, unremarkable. The road is wide. The deck is solid. The cable-stayed structure provides ample clearance and visible reassurance of its structural confidence. But the 1980 disaster is not forgettable context. It is immediate physical reality that every regular user of the bridge carries with them. The memorial installed at the old bridge's approach, the dedicated section of the original structure preserved as a fishing pier and memorial walkway, is visible from the new bridge as you cross. The 430-foot towers that the architects designed to be beautiful are also the product of a very specific engineering decision made in direct response to 35 specific deaths. The Sunshine Skyway is a monument to the consequences of underestimating natural conditions. The original bridge was not poorly built. It was well built for the conditions its designers anticipated. What they failed to fully anticipate was MV Summit Venture in zero visibility conditions on May 9, 1980. The replacement bridge anticipated it. Every design decision, every engineering specification, every protective measure on the current structure is a response to that specific failure. It is a bridge built by grief and engineering in equal measure. Burj Khalifa, UAE. It pierces the clouds, a silver needle stitching the sky to the sands of Dubai. The Burj Khalifa is not just a building, it is the ultimate statement of human ambition. Standing at a staggering 2,717 feet, over half a mile high, it is the tallest structure ever built by human hands. It is 3 times as tall as the Eiffel Tower and nearly twice as tall as the Empire State Building. To stand at its base is to feel impossibly small. To look down from its summit is to see the world like a god. Completed in 2010, it remains the undisputed king of the skyline, holding over a dozen world records, including the highest occupied floor and the elevator with the longest travel distance. The engineering required to build this vertical city is mind-boggling. The tower's design is based on the Hymenocallis flower, utilizing a Y-shaped buttressed core system. This three-winged footprint provides maximum stability against the ferocious desert winds and gravity itself. As the tower rises, it sets back in a spiraling pattern, confusing the wind and preventing the formation of organized vortexes that could rock the building. Over 430,000 cubic yards of concrete and 39,000 tons of steel rebar were used. The concrete had to be pumped to record-breaking heights, a task so difficult it could only be done at night when temperatures were cooler to prevent the mix from setting too quickly. Inside, the Burj Khalifa is a vertical luxury liner. It houses the Armani Hotel, corporate suites, and residential apartments where people live amongst the clouds. The exterior is clad in 26,000 reflective glass panels, hand-cut and designed to withstand the intense Arabian heat. Keeping it clean requires a fleet of brave window cleaners who dangle from the heavens. At night, the tower transforms into the world's tallest LED screen, pulsating with light shows that can be seen from miles away. The Burj Khalifa is the anchor of downtown Dubai, a symbol of the region's rapid transformation from a pearl-diving outpost to a global metropolis. It is a testament to what happens when unlimited vision meets cutting-edge engineering. It is proof that we can conquer the vertical frontier, pushing the limits of physics to touch the stars. It stands as a beacon of possibility, a silver giant watching over the desert. Millau Viaduct, France. Soaring above the clouds in southern France is a bridge that looks more like a work of art than a highway. The Millau Viaduct is the tallest bridge in the world, with one of its masts rising 1,125 feet, taller than the Eiffel Tower. Spanning the Tarn Valley, this cable-stayed masterpiece solved a notorious traffic bottleneck on the route from Paris to Spain. But instead of a clunky concrete overpass, British architect Norman Foster and French engineer Michel Verlojux created a delicate white line that floats effortlessly across the landscape. It touches the valley floor in only 9 places, minimizing its impact on the environment. Constructing this giant required cutting-edge techniques. The 7 massive concrete piers were built first, rising like ancient monoliths. Then, the steel roadway, weighing 36,000 tons, was not lifted but launched. Hydraulic rams pushed the deck out from both sides of the valley, meeting in the middle with millimeter precision. This incremental launching method was a high-stakes operation performed hundreds of feet in the air. The pylons above the road were then erected, and the cables strung to support the deck. The bridge is designed to withstand wind speeds of up to 150 km/h, with an aerodynamic shape that slices through the air like an airplane wing. Driving across the Millau Viaduct is an ethereal experience. On foggy days, the valley floor disappears, and you feel as though you are flying. The bridge is slightly curved, a deliberate design choice to give drivers better visibility and prevent the monotony of a straight line. It has turned a traffic jam into a tourist attraction, with a visitor center that draws enthusiasts from around the globe. The Millau Viaduct is the pinnacle of modern civil engineering. It combines brute strength with impossible lightness. It proves that functional infrastructure can enhance the natural beauty of a landscape rather than detract from it. It is a thread of steel and concrete sewing together the north and south of Europe, standing as a monument to elegance and precision. Delta Works, Netherlands. The Netherlands is a nation built on a challenge. Much of its land lies below sea level. In 1953, a catastrophic flood claimed over 1,800 lives, proving that the old dikes were not enough. The response was the Delta Works, a massive series of construction projects often called the eighth wonder of the world. It is the largest flood protection system on the planet, a complex network of 13 dams, storm surge barriers, and dikes designed to seal off the river mouths of the Rhine, Meuse, and Scheldt from the wrath of the North Sea. It is humanity's boldest defense against the ocean. The crown jewel of the Delta Works is the Oosterscheldekering Eastern Scheldt Storm Surge Barrier. Unlike a solid dam that would destroy the saltwater tidal ecosystem, this barrier is movable. It consists of 62 massive steel gates sliding between 65 concrete pillars. Under normal conditions, the gates stay open, allowing tides to flow and preserving the marine environment. But when a storm hits, the gates drop, turning into an impenetrable wall of steel against the surging waves. The pillars are so huge that each one weighs 18,000 tons, and they had to be placed on the sandy sea floor using specialized ships and seabed mats to prevent shifting. Another marvel is the Meeslantering, a barrier with two massive swinging arms, each as long as the Eiffel Tower is tall. When a storm approaches, these arms swing out from the river banks, meet in the middle, and sink to form a dam. It is entirely computer-controlled, making life-or-death decisions without human intervention. The project shortened the Dutch coastline by 700 kilometers, drastically reducing the risk of flooding. The Delta Works is a testament to Dutch ingenuity and survival. It shows that we cannot conquer nature, but we can negotiate with it. As sea levels rise due to climate change, the world looks to the Delta Works for lessons in resilience. It is a shield of concrete and steel that allows a nation to sleep soundly beneath the level of the waves. Gardens by the Bay, Singapore. Step into a sci-fi jungle where nature and technology fuse into a vibrant green explosion. Gardens by the Bay in Singapore is not just a park. It is a 250-acre horticultural wonder that redefines the concept of a garden city. Its most recognizable feature is the super tree grove. These 18 tree-like structures rise up to 164 feet tall, dominating the skyline like alien flora. But they aren't just sculptures. They are vertical gardens covered in over 162,900 plants, bromeliads, orchids, and ferns that crawl up their steel skin. At night, they come alive with the Garden Rhapsody, a dazzling light and sound show that feels straight out of the movie Avatar. The engineering behind these gardens is focused on sustainability. Some super trees are fitted with photovoltaic cells to harvest solar energy, which powers the lights at night. Others serve as air exhaust vents for the two massive conservatories nearby. Speaking of which, the Flower Dome and the Cloud Forest are marvels in themselves. They are the world's largest glass greenhouses without columns, using a spectrally selective glass to let in light while keeping out heat. Inside the Cloud Forest, a 115-foot man-made mountain features the world's tallest indoor waterfall, surrounded by mist-filled walkways that simulate a tropical highland climate. The gardens were built on reclaimed land, transforming a barren waterfront into a lush ecosystem. The cooling systems are powered by biomass, burning horticultural waste to generate energy. The entire site acts as a giant sponge, capturing rainwater and cleansing it through aquatic reed beds before releasing it into the reservoir. It draws millions of tourists annually, offering a cool respite from Singapore's humidity. Gardens by the Bay is a vision of the future where urban density and nature coexist. It teaches us that technology doesn't have to replace the natural world, it can enhance and protect it. It is a stunning example of bioarchitecture, proving that even in a concrete metropolis, life can bloom in the most spectacular ways. The Straits of Mackinac, the narrow water connection between Lake Michigan and Lake Huron, is one of the most meteorologically complex inland waterway environments in North America. In winter, ice forms on the straits in patterns determined by temperature gradients, wind direction, and the complex interaction of two Great Lakes mixing at a narrow point. In summer, fog can descend with nearly no warning and reduce visibility to zero in minutes. In autumn, the Great Lakes generate storms, freshwater hurricanes, some call them, whose wind speeds and wave heights bear no resemblance to the calm lake surface that summer tourists photograph. And across this environment, the Mackinac Bridge has been standing since 1957. The Mackinac Bridge, the mighty Mac, stretches approximately 5 miles between Mackinac City on the Lower Peninsula and St. Ignace on the Upper Peninsula. The suspended portion of the bridge is the longest in the Western Hemisphere, approximately 3,800 feet of cable-supported deck, hanging from 2 towers rising 552 feet above the water. The main cables consist of tens of thousands of individual steel wires, each one woven into a 24.5-inch diameter strand that carries a portion of the total load. The total steel wire used in the 2 main cables would, if unraveled and stretched out, extend approximately 42,000 miles, more than 1.5 times around the Earth. The central section of the Mackinac Bridge deck is open grating rather than solid concrete. This is not an accident, and it is not a budget decision. It is a specific engineering response to the wind conditions in the Straits of Mackinac. A solid deck at this location and elevation would catch the wind like a sail and impose enormous lateral forces on the cable system. The open grating allows wind to pass through the deck surface, dramatically reducing the force applied to the structure while simultaneously creating the experience for drivers of seeing the water 200 feet below through the road surface beneath their tires. In strong crosswinds, the deck moves, visibly, detectably. In the steering wheel and in the body, some drivers request escort services. The Michigan Department of Transportation will drive vehicles with anxious drivers across the bridge in certain weather conditions. This is a real service. It is used. It is not embarrassing. The Mackinac Bridge in a strong crosswind is a physical experience that does not require a history of anxiety to find genuinely demanding. The photograph was taken from a specific position on the Atlantic Ocean Road in Møre-og-Romsdal County, Norway, using a telephoto lens aimed at a bridge in the middle distance. The photograph shows a road that rises to a peak, curves slightly to the right, and then appears to end, to simply stop, with nothing visible beyond the curve except sky. It looks like a road being built to launch something into the air. It looks like the beginning of a ramp to nowhere. It looks, in the specific and disorienting way of the best optical illusions, like an error in the design of reality. The Storsøysundet Bridge does not end in the sky. The road continues on the other side of the crest, descending to the next island in the Atlantic Ocean road chain, a series of 8 bridges and connected islands that stretch across the Norwegian Sea between Molde and Kristiansund. The illusion, which is genuine and visible from the road, as well as in photographs, though the full force of it requires the right angle and the right moment, is created by the combination of the bridge's S-curve design, the camber of the roadway, and the perspective effects of the surrounding open ocean, which provides no consistent visual reference for scale or distance. The Storsøysundet Bridge was listed by BBC Top Gear in 2011 as one of the most dangerous roads in the world. The listing was based not on accident statistics, but on the character of the driving experience. The tight curves, the low barriers, the direct exposure to North Atlantic weather, and the wave wash that, during significant storms, crosses the roadway surface. The bridge does not have emergency pedestrian lanes. The roadway has no dedicated protection from the side winds that come off the Norwegian Sea at velocities that require active steering correction. And the waves, the North Atlantic waves that have been building since the coast of Canada, arrive at the Storsøysundet Bridge with no attenuation. When conditions are severe, seawater reaches the road surface and the bridge becomes, temporarily, a surface through which moving water and moving vehicles share the same space. Audi selected the Storsøysundet Bridge as a test site for their body stabilization systems. This is a meaningful data point. Automotive engineers, tasked with finding conditions extreme enough to demonstrate their technology's value under real-world stress, chose this bridge. not a laboratory, not a controlled test track. This specific bridge in real Norwegian weather, where the conditions exceed what any controlled environment can replicate. This is the foundational premise of bridge design. The structure exists to span a gap that cannot otherwise be crossed. The Twist, opened in 2019 at the Kistefos Museum in Jevnaker, Norway, crosses a river. That function is real, but describing the Twist solely as a river crossing is like describing the Sagrada Familia solely as a church. The description is accurate. It entirely misses the point. The Twist is a bridge that rotates 90 degrees along its length. It spans 60 meters, approximately 200 feet, across the Ranselva River, connecting two sections of the Kistefos Sculpture Park on opposite banks. As visitors walk from one end to the other, the floor, walls, and ceiling of the structure gradually rotate around them. What begins as floor is ceiling by the end. What begins as a right angle to the bank is an entirely different orientation at the midpoint and a different orientation again at the far end. The crossing is approximately 60 meters long. The full structural rotation is 90 degrees. The spatial disorientation produced by this geometry is not metaphorical. It is physical, immediate, and for many visitors, genuinely difficult to process while walking through it. The design by Bjarke Ingels Group, the Danish architecture firm, was driven by a practical engineering problem presented by the terrain. The two banks of the Ranselva at this location sit at different elevations. A conventional horizontal bridge would require one end to be lower than the other, producing a ramp. The Twist responds to this elevation difference through rotation. By twisting the structure, the floor and the structural members absorb the level change as a gradual transition rather than an abrupt grade. The geometry is the solution. The disorientation is the byproduct. The exhibition spaces that occupy the bridge interior, the Twist functions simultaneously as a crossing, a gallery, and an architectural experience, are the context that makes the disorientation meaningful rather than merely confusing. The Kistefos Museum is a sculpture park built around a former pulp mill, and it has become internationally recognized for the quality of its commissioned art and architecture. The Twist, as both bridge and gallery, is the centerpiece, an object that you walk through and across simultaneously, that resolves an engineering problem through architectural boldness, and that delivers, on the other side, the specific pleasure of having your spatial comprehension briefly, productively disrupted. Not every bridge needs to be crossed in a straight line. If you approach the Nanpu Bridge from the Pudong side of the Yangpu River on a clear morning, the first thing you notice is the spiral, not the cable-stayed span itself, though that is imposing. Its towers rising nearly 350 feet above the river, but the approach ramp, a coiled concrete helix 5 complete turns rising to bridge deck height, carrying 3 lanes of Shanghai traffic up from street level in a tight circular path that from above looks like the architectural equivalent of a clenched fist. This spiral is simultaneously Nanpu's most celebrated visual element and one of its most genuinely dangerous features. The Nanpu Bridge was completed in 1991 as part of Shanghai's rapid infrastructure expansion during the Pudong development era. It was the first cable-stayed bridge across the Yangpu River, replacing ferry crossings that had become completely inadequate for the volumes of traffic the developing city was generating. The cable-stayed design allows the main span, approximately 423 meters, to cross the river with no piers in the water, preserving navigational clearance for the continuous heavy shipping traffic that uses the Yangpu as one of China's primary commercial waterway arteries. The spiral ramp exists because the bridge must rise steeply from street level to deck height, and the spiral geometry allows that ascent within a small land footprint in an extremely dense urban environment. The engineering of the spiral is sound, but the operational reality tracks longer than 20 meters in the constrained geometry of a continuous circular ramp at speeds that are sometimes higher than the geometry safely permits, has produced an ongoing record of incidents. Vehicles lose the line on the tightest curves. Loads shift on trucks navigating the constant centripetal acceleration. The margins for error on a 3-lane spiral ramp with no runoff areas are not generous. Civil Engineering magazine ranked the Nanpu Bridge among the top 10 most dangerous urban bridges in the world. The ranking reflects not just the spiral ramp, but the broader operational reality of the bridge. Founded on the soft alluvial soil of the Yangpu Delta, requiring over 20 deep piles extending 40 meters into the ground for foundation stability. Subject to the dynamic loads of Shanghai's never-diminishing traffic for over 30 years, and historically recording over 700 technical incidents and minor accidents. When incidents occur on the spiral, emergency access requires vehicles to ascend the ramp from ground level, a response time that adds a practical consequence to the theoretical one. There is a category of engineering record that measures not the size of a thing, but the speed of a thing, not how large a structure was built, but how fast it was assembled. The Lupu Bridge across the Yangpu River in Shanghai holds a record in this category, the assembly of its main steel arch, a span of 550 meters. The longest steel arch bridge span in the world at the time of its completion in 2003 was completed using a hydraulic lifting system that raised the final central sections into position in approximately 70 minutes, not 70 days, not 70 hours. 70 minutes, in which 550 meters of steel arch was joined and tensioned and made complete above one of the most heavily trafficked inland shipping corridors in the world. The Lupu Arch carries 6 lanes of road traffic at a deck height sufficient for the large vessels that use the Yangpu. There are no piers in the river. The arch, as with all true arch bridges, transfers its load entirely through compression into the abutments at both riverbanks, leaving the 550-meter span below completely clear. This is an engineering commitment. No intermediate supports means the structure is in a state of constant, fully distributed maximum stress. Every vehicle on the bridge contributes to the total load carried by the arch. Every thermal cycle, the expansion and contraction of steel across Shanghai's seasonal temperature range, adds stress cycles to the arch material. The arch is not merely holding still. It is working continuously under the full weight of its commitment. The Lupu Bridge has a pedestrian access to the top of the arch, a stairway that climbs from bridge deck level to the arch crown, approximately 105 meters above the Yangpu. From the top of the arch, the river, the city, and the adjacent Nanpu Bridge spiral ramp are all visible in a panorama that, on clear days, extends to the entire Pudong skyline. Standing at the arch crown, the width of the river and the density of the city surrounding it communicate the full scale of the engineering challenge that the Lupu was built to address. And the knowledge that you are standing on the highest point of 550 meters of steel arch that was raised to this position in 70 minutes, above a river where cargo vessels pass 100 meters below your feet, is not abstract. It is immediate, vertical, and real. The Shard, UK. Rising from the south bank of the Thames like a jagged piece of glass, piercing the London fog, the Shard is a vertical city that changed the face of the British capital. Standing 1,016 feet tall, it is the tallest building in the United Kingdom and Western Europe. Designed by Renzo Piano, it was inspired by the spires of London's historic churches and the masts of tall ships that once crowded the river. Its pyramidal shape is elegant and sharp, clad in 11,000 panels of glass, enough to cover 8 football pitches. These panels reflect the sky, making the massive tower change mood with the weather, blending into the atmosphere. Building a skyscraper in London is a logistical nightmare. The site was small, triangular, and surrounded by a busy hospital and a major train station. To speed up construction, engineers used a revolutionary top-down method. They dug the foundations while simultaneously building the core upward, a first for the UK. The spire at the top was constructed from prefabricated steel sections, assembled by a crane that seemed to hang in midair. The shard edges at the top are open to the elements, allowing the building to breathe and giving the summit a crystalline, unfinished appearance. Inside, the shard is a mixed-use marvel. The lower floors house offices, followed by world-class restaurants, the Shangri-La Hotel, and luxury residences that offer the best views in the city. At the very top, the view from the shard offers a 360-degree panorama stretching for 40 miles. You can see the twists of the Thames, the Tower of London, and the distant hills, all from 72 floors up. The shard faced criticism for its size and modernity in a historic city, but it has become a beloved landmark. It symbolizes a modern, confident London. It is not just a tower, it is a beacon. At night, its tip glows, acting as a lighthouse for the city. It demonstrates that modern architecture can respect history while boldly asserting its place in the future. Petronas Towers, Malaysia. In Kuala Lumpur, two silver giants hold hands across the sky. The Petronas Towers are the twin jewels of Malaysia, capturing the world's attention when they became the tallest buildings on Earth in 1998, a title they held until 2004. Standing 1,483 feet tall with 88 stories, they remain the tallest twin towers in the world today. Designed by Cesar Pelli, their architecture is distinctly Malaysian, blending modern technology with Islamic motifs. The floor plan is based on an 8-pointed star, a symbol of harmony and stability, while the facade of stainless steel and glass reflects the tropical sun like a diamond. The construction was a race against time and geology. Two different construction consortiums, one Japanese, one South Korean, were hired to build one tower each, creating a fierce competition to finish first. But early on, a major problem arose. The site sat on an irregular bedrock of limestone and soft soil. To prevent the towers from tilting, engineers moved the entire foundation and drove the world's deepest concrete piles, extending 400 feet into the ground. This forest of friction piles supports the immense weight of the towers. The defining feature is the Skybridge on the 41st and 42nd floors. This double-decker bridge is not rigidly attached. Instead, it slides in and out of the towers on bearings. This engineering genius allows the towers to sway independently during high winds without snapping the bridge. It serves as a viewing platform and an emergency exit route between buildings. At the base lies Surya KLCC, a luxury mall, and a beautifully landscaped park that acts as the green lung of the city. The Petronas Towers put Kuala Lumpur on the global map. They symbolize Malaysia's rapid modernization and ambition. At night, they glow like two silver pagodas, visible from almost anywhere in the city. They are a testament to cultural identity expressed through high-tech architecture, proving that skyscrapers can have a soul. Itaipu Dam, Paraguay, Brazil. Straddling the border between Brazil and Paraguay on the Paraná River lies a concrete monster, the Itaipu Dam. For decades, it was the largest hydroelectric producer in the world. It is a joint venture between two nations, a diplomatic and engineering marvel that generates a staggering amount of energy. The dam stretches nearly 5 miles across and stands 643 feet tall, equivalent to a 65-story building. The amount of concrete used to build it could have built 210 football stadiums. The steel used could have built 380 Eiffel Towers. Began in the 1970s, the project required diverting the mighty Paraná River. Workers carved a 13-mile diversion channel through solid rock, the biggest diversion in history. Then, the dry riverbed became the construction site. The dam houses 20 massive turbines, each capable of generating 700 megawatts. When running at full capacity, Itaipu produces 14,000 megawatts. It provides about 90% of the electricity consumed by Paraguay and roughly 15% of Brazil's energy. It is the beating heart of two economies. The spillway is a spectacle of its own. When the reservoir gets too high, the gates open, releasing water at a rate 40 times the flow of nearby Iguazu Falls. The water launches off a ski jump ramp, soaring into the air to dissipate energy before crashing back into the river, preventing erosion at the dam's base. The reservoir created by the dam is 100 miles long, a massive inland sea. Itaipu is a controversial giant. Its creation displaced thousands of people and submerged natural wonders like the Guarira Falls. Yet, it is hailed as one of the 7 wonders of the modern world by civil engineers. It is a powerhouse of clean energy, a colossal battery that keeps the lights on for millions. It stands as a brute force example of how humanity harnesses the raw power of nature. Aqueduct of Segovia, Spain. In the heart of Segovia, Spain, a stone giant strides through the city. The Aqueduct of Segovia is one of the most significant and best-preserved ancient monuments on the Iberian Peninsula. Built by the Romans around the 1st century AD, likely under Emperor Trajan, it carried water from the Frio River 10 miles away to the city's hilltop fortress. What makes it a miracle is that it stands without a single drop of mortar. No cement, no glue, just physics. The structure spans 2,600 feet across the city, rising to a height of 93 feet at its peak in the Plaza del Azeguillo. It consists of 167 arches constructed from 20,400 massive blocks of granite. The stones are stacked with such perfect balance and precision that they have held together for 2 millennia through wars, earthquakes, and modern pollution. The arches are divided into 2 tiers, giving the structure elegance and stability. The builders used wooden centering frames to hold the arches in place until the keystone was dropped, locking the compression forces. The aqueduct functioned for centuries, supplying water until the mid-19th century, an operational lifespan of nearly 1,800 years. Legend says it was built by the devil in a single night to win a girl's soul, but the holes in the stones tell a different story. They are marks from the Roman lifting tongs used to hoist the blocks. In 1992, cars were banned from driving under it to protect it from vibration and exhaust fumes. The Aqueduct of Segovia is a masterpiece of civil engineering. It dominates the skyline, dwarfing the buildings around it. It is a testament to the Roman obsession with utility and durability. It stands as a silent witness to history, held together not by chemical bonds, but by the sheer genius of balance. The Trift Glacier in the canton of Bern, Switzerland, has been retreating for approximately 150 years, but the pace of that retreat has accelerated dramatically within living memory. In the early 2000s, the glacier had pulled back far enough to expose a new lake at its snout, separated from the main glacier body by a rocky valley that had been hidden beneath the ice for thousands of years. The natural ice bridge that had previously connected the valley sides disappeared as the glacier retreated above it. And the hiking route that traversed the glacier, a classic alpine traverse used by experienced mountaineers for generations, was suddenly broken, the route interrupted by a newly exposed void that the disappearing ice had left behind. The response was the Trift Bridge, a suspension bridge installed across the newly exposed glacier valley in 2004, providing the traverse route's missing link in 170 meters of steel cable and aluminium deck. The statistics are immediately significant. The bridge stands 100 meters above the valley floor, spans 170 meters, and hangs in an alpine environment where the glacier lake, formed by meltwater from the retreating Trift Glacier, is directly visible below during the crossing. The lake is a vivid, unnatural shade of turquoise blue, the color produced when light interacts with the fine sediment particles that glacial meltwater carries. A color that is beautiful and which, in its very existence, represents the physical destruction of the ice that once made the bridge unnecessary. The 2004 version of the bridge had a problem that became apparent quickly: significant oscillation when multiple people were on the structure simultaneously. Alpine suspension bridges in windy environments are subject to resonance, the same phenomenon that destroyed the first Tacoma Narrows Bridge, and the Trift Bridge's initial design was not fully damped against this risk. After strong oscillations were reported and documented, the bridge was taken down and a fully redesigned replacement was installed in 2009, with damping systems specifically engineered to prevent the resonance behavior that had made the first version feel, in the description of some crossers, genuinely alarming. The replacement bridge resolves the oscillation problem without resolving the fundamental nature of the experience. You are still 100 meters above a glacial lake crossing a valley created by retreating ice. With exposed bedrock polished to a high sheen by the glacier that has since abandoned it visible on the slopes below. The boulder fields left behind, moraines deposited, and then stranded by the retreating Trift Glacier provide a geological record of the ice's former extent. The bridge crosses the gap the ice left behind. Every year, as the glacier retreats further, the scenery around the bridge changes slightly. The lake is slightly larger. The exposed bedrock extends slightly further. The Trift Bridge is crossing a landscape in the process of being transformed, and the transformation is not finished. Not every bridge on this list is dangerous because of height or exposure or structural risk. The Rakotzbrücke or Rakotzbridge, sometimes called the Devil's Bridge, in Kromlauer Park in the Görlitz district of Saxony, Germany, occupies a different category entirely. The category of bridges dangerous to the mind, to perception, to the comfortable distinction between the real and the impossible. Because the Rakotzbrücke was designed, from the beginning, to create a visual experience that should not be possible, and which, when conditions are right, is so complete and so convincing that standing before it produces a species of disorientation that more conventionally dangerous bridges rarely achieve. The bridge was built in the 1860s on the estate of Friedrich Hermann Röhrschke, who designed the surrounding park as a landscape garden in the Romantic tradition, a tradition that sought to create natural scenes more beautiful and more emotionally affecting than actual nature through careful design planting and placement of architectural elements. The Rakotzbrücke was the centerpiece of this vision, a slender stone arch, approximately 35 feet high, spanning a small lake, designed to be seen from a specific viewpoint across the water. From that viewpoint, when the water is still, which it is most commonly in early morning, before wind disturbs the surface, the arch and its reflection form a perfect circle, not an approximate circle, not a suggestive oval. A precise, geometrically complete circle, half above the water and half below, complete and continuous and entirely convincing. The technical requirement for this visual effect is demanding. The arch must be precisely semicircular. Any departure from a true half circle destroys the geometry of the reflection. The water surface must be at exactly the right level relative to the arch springings. If the water is too low, the reflected arch hangs in space above the real one. If too high, it appears to overlap. The viewpoint from which the observation must be made is specific. The reflected circle is only fully complete from one position on the lakeshore. All of these requirements were incorporated into the bridge's design in the 19th century with precision that speaks to both the craftsmen who built it and the designer who conceived it. The Rakotzbrücke is not open to pedestrian traffic. Walking on, it is prohibited to preserve the structure. It exists purely to be seen in the specific way its designer intended, from the specific angle that completes its geometry at the specific time of day when the water is still enough to function as a mirror. In a list of bridges that test physical courage, the Rakotzbrücke tests something different: the capacity to process visual information that the rational mind knows cannot be correct, and to allow that impossibility to be experienced fully, without explanation, as a form of beauty that transcends ordinary classification. Dragon Bridge, Da Nang, Vietnam. At 9 p.m. on weekend evenings in Da Nang, Vietnam, something happens on the Han River that exists nowhere else in the world, and that visitors who have not been warned about it can find, depending on their proximity, either spectacular or genuinely alarming. The Dragon Bridge breathes fire. A programmed sequence of ignited fuel, controlled by remote systems integrated into the bridge's steel dragonhead pylon at the eastern end of the structure, produces a jet of real fire from the dragon's mouth, accompanied by a jet of water from the same source in alternating sequence. Illuminated from below by the bridge's LED system, visible from considerable distance across the river and the city, the Dragon Bridge was completed in 2013 to connect Da Nang's urban center with its coastal resort district. Spanning the Han River in a design whose primary structural element is a steel arch shaped as a dragon, the same symbol that historically represents the divine protection of the kings of Vietnam, and that the early settlers of the Da Nang region believed to have emerged from this specific section of the Han River. The bridge is 666 meters long with a 200-meter main span, carrying 6 lanes of road traffic plus 2 footways. Its engineering is conventional cable and deck construction beneath the theatrical exterior. The Dragon is a shell, decorative steel panels over a structural frame, but the fire is real. The fire display creates a specific safety management challenge. The area of the bridge around the Dragon Head during the fire sequence becomes extremely hot enough that the drainage and ventilation systems for the fuel and combustion products require careful engineering to prevent heat damage to structural components. During major holidays, when visitor numbers on the bridge have exceeded 10-0 simultaneously, the fire display happens while large crowds are on the structure. A crowd density that, combined with the fire and the marine coastal weather that Da Nang frequently experiences, creates a risk management scenario that requires a dedicated response team. The bridge has emergency protocols specifically for the fire display. These are used, they are tested. They exist because a bridge with a fire-breathing dragon pylon carrying 10,000 people is a structure for which standard emergency planning is insufficient. When the Stonecutters Bridge opened in 2009, it connected Stonecutters Island to the Tsingyi area across Rambler Channel in one of the most logistically complex harbor environments in Asia. 2 cable-stayed towers rise 298 meters from the water, among the tallest bridge towers in the world, supporting a main span of 118 meters across a deepwater channel that is at this location one of the primary approaches to the Quai Tsing container terminal. The world's busiest container port by annual throughput, the ships that pass beneath the Stonecutters Bridge are not the largest in the world, but they are among the most economically significant vessels whose schedules are measured in days and whose deviation from those schedules is measured in millions of dollars. The cable-stayed system of the Stonecutters Bridge incorporates an automatic cable adjustment mechanism, a real-time structural monitoring and response system that detects changes in cable tension caused by temperature variation, wind loading, and traffic patterns, and adjusts the cable geometry incrementally to maintain the intended structural configuration. The bridge is, in a meaningful sense, constantly correcting itself. The deck position that you drive across is not the deck position that was designed and installed at completion. It is the deck position that the monitoring system has continuously maintained through thousands of incremental adjustments over the years since opening. The visual disappearance of the towers into Hong Kong's harbor mist, a phenomenon documented by the Bridges Management Authority as a navigation concern for drivers approaching in low visibility, is not merely aesthetic. The steel gray of the tower surfaces against Hong Kong's frequent marine fog layer creates a contrast profile that can be insufficient for drivers to acquire a clear visual reference during approach. The Bridge Management Authority has installed additional lighting specifically to address this condition. Even so, drivers approaching in fog report the specific disorientation of seeing the bridge deck emerge from mist without being able to orient relative to the tower position, arriving at the bridge without the visual context that normal visibility provides. The central span of the Cap Shui Mun Bridge stretches 430 meters above one of the most contested pieces of water in Hong Kong, the Cap Shui Mun Channel between Tsing Yi and Ma Wan, through which a shipping route of international significance passes continuously. This is a bridge that must coexist daily and permanently with vessels whose physical scale approaches its own. Container ships with beam widths exceeding 40 meters transit below a cable-stayed bridge whose towers are separated by 430 meters of main span. The towers visible simultaneously to the bridge of a large vessel making the transit. The deck above representing the upper limit of the vessel's available air draft. The Cap Shui Mun Bridge is a double-deck structure, road traffic on the upper deck, mass transit railway airport express, and Tung Chung Line rail services on the lower. The lower deck is enclosed to protect rail infrastructure from wind and spray, a design requirement that emerged from wind tunnel testing that revealed the aerodynamic characteristics of the lower deck in open configuration would create unacceptable lateral oscillation under strong typhoon winds. The enclosure solves the wind problem and introduces a different one. The lower deck is a confined enclosed space with no pedestrian escape route through which MTR trains pass above sea level in conditions that can include typhoon-force winds, strong current flows visible through the structure's seams, and the occasional passage of a very large ship close enough below to affect the perceptible vibration environment inside the tunnel. The psychological experience of crossing the Cap Shui Mun Bridge is defined by the combination of scale, the main span, length, the tower height, the vessel traffic below, and the knowledge for any informed driver that the single lower deck carries both of Hong Kong's primary rail routes to the airport. The bridge is not merely a crossing. It is a critical node in the transport infrastructure of an international city, carrying 60,000 daily journeys on the rail level and continuous road traffic above, on foundations anchored into complex seabed geology in an active shipping channel. Its criticality is its specific and unrelenting form of danger. This is not a bridge that can fail quietly. Passage du Gois, France. Passage du Gois is a road unlike any other on Earth. This 412 km causeway connects Noirmoutier Island to mainland France, but its danger comes from the tides. Twice a day, the Atlantic Ocean swallows it entirely, leaving only a narrow window for crossing. If you mistime your journey, your car can become a temporary submarine in waters up to 4 meters deep. The surface is slippery, covered with green moss and mud that conceals potholes and uneven patches. Even on a clear day, waves can crash onto the asphalt, threatening vehicles with sudden, unexpected force. Locals respect it, but tourists often underestimate the timing and risk. The psychological pressure is immense. Every second counts, hesitation can be fatal. Drivers must calculate tides precisely, monitor water levels, and navigate the slick causeway with unwavering focus. One misjudgment, and the vehicle can be carried away by the rising water. Passage du Gois is a unique combination of natural danger and precision. It's not long, but it demands absolute attention, courage, and respect for the unpredictable ocean. Every crossing becomes a high-stakes test of nerve and timing, leaving a lasting impression on those brave enough to attempt it. Stelvio Pass, Italy. The Stelvio Pass, high in the Italian Alps, is a road that redefines the word hairpin. With 48 numbered stone curves on the northern side alone, The pass snakes up to 2,757 meters in altitude, twisting relentlessly around the mountain as if testing the limits of human skill. From above, it resembles a coiled serpent. From behind the wheel, it is a continuous, dizzying battle. Each tight curve demands precise steering, careful braking, and attention to the gradient. Vehicles often scrape their undercarriage on sharp bends, and trucks must sometimes reverse to navigate the tightest corners. Weather amplifies the danger. Snow can appear suddenly even in late spring, rain makes the asphalt slick, and fog can reduce visibility to near zero. Accidents are frequent, some fatal, leaving clear evidence of the pass's perils. Drivers must master engine braking and anticipate every incline and turn. Despite the risks, Stelvio Pass is legendary for its breathtaking views. Glaciers, valleys, and alpine peaks unfold with every bend. But beauty comes at a price. One small error in judgment can send a car tumbling down steep cliffs, turning the journey into a literal nightmare. Stelvio is not just a road. It is a test of nerve, precision, and endurance. Every driver who takes it on knows the adrenaline, respect, and awe it demands. This pass is a high-altitude ballet of metal, gravity, and human courage. Los Caracals Pass, Chile, Argentina. Los Caracals, or the Snails, is aptly named for its spiral-like curves stacked upon each other like a snail's shell. Located in the Andes, this pass climbs above 3,000 meters, forcing vehicles to twist relentlessly along hairpins with sheer cliffs on one side and ravines hundreds of meters deep on the other. The road is unforgiving. Heavy snowfall in winter turns the asphalt into a treacherous ice rink, while steep inclines challenge engine power and brake endurance. Trucks carrying containers or goods must proceed with extreme caution. One brake failure or engine stall can trigger disaster. Drivers must remain alert, with hands constantly on the wheel and eyes never leaving the road. Fog, snow, and icy patches add to the peril. Even for experienced drivers, Los Caracals is a high-stakes journey where survival hinges on skill, patience, and nerve. Yet the scenery is awe-inspiring: jagged Andean peaks, deep valleys, and the sheer thrill of navigating one of the most challenging passes on the continent. Los Caracals combines breathtaking beauty with life-or-death danger, making it a road that tests every fiber of a driver's courage and control. Rotang Pass, India. Rotang Pass, at roughly 3,978 meters above sea level, connects Manali to the Lahaul-Spiti region and is notorious for accidents and harsh conditions. The road winds through hundreds of hairpin bends, many so narrow that two vehicles cannot pass simultaneously, and a sheer cliff drops into nothingness beside every turn. Weather is a constant adversary. Heavy snowfall, landslides, and sudden rain transform the road into mud or ice. Vehicles struggle for traction, and overconfidence is often punished with loss of control. Traffic congestion has worsened in recent years, creating hours-long jams where vehicles inch forward along narrow, dangerous stretches. Psychologically, Rotang tests nerve and focus. Drivers must anticipate slides, reverse carefully around blind bends, and manage brakes and gears under extreme stress. Despite its beauty, snow-capped peaks, glacial rivers, and alpine valleys, the pass commands respect and caution. Rotang Pass is a trial of skill, endurance, and courage. One lapse can be fatal, and every journey demands maximum attention. For drivers, it is a combination of awe and anxiety, where natural beauty and mortal danger coexist in every bend. Zojila Pass, India. Zojila, rising to over 3,500 meters in the Himalayas, is a lifeline connecting the Kashmir Valley with the remote Ladakh region. The road is carved into steep mountain slopes, often barely wide enough for a truck. On one side, sheer cliffs; on the other, bottomless drops. Surface conditions are brutal. Snowmelt and rain make dirt, gravel, and mud treacherous. Vehicles slip, brakes fail, and drivers must execute turns with precision and patience. Oncoming traffic requires tense negotiations, often forcing one vehicle to reverse along a cliff edge for hundreds of meters. The psychological and physical strain is immense. High altitude makes breathing laborious, reaction times slower, and attention harder to maintain. One split-second error can send vehicles plummeting into the abyss. Zojila is more than a road. It is a battlefield of nerves, endurance, and skill. Only experienced drivers can navigate it safely, where every bend is a test and every journey an epic struggle against nature's raw power. The pass is unforgiving, awe-inspiring, and a true measure of courage. Los Caracoles Pass, Chile, Argentina. From above, it looks like a spiral carved into the Andes. Los Caracoles, meaning the snails, earns its name from the tight, stacked hairpin bends that coil up the mountainside near the Chile-Argentina border. Located at over 3,000 meters above sea level, this pass is a crucial connection between the two countries. But crossing it feels like climbing a concrete staircase into thin air. The bends are relentless, one after another, each nearly 180 degrees. Drivers must slow drastically, then accelerate uphill again, repeating the cycle dozens of times. Heavy container trucks dominate this route. Now imagine one of those massive vehicles attempting a tight hairpin on a steep incline. Engines strain, gears grind, brakes heat up. In winter, snow blankets the road. Ice forms silently in shaded corners. Chains are often required. Strong Andean winds push against tall vehicles, threatening balance mid-turn. Guardrails exist in many areas, but not all. And even where barriers stand, they are no guarantee against the weight of a fully loaded freight truck losing braking power. Traffic congestion adds pressure. When one vehicle struggles on a climb or experiences mechanical failure, the entire pass can become gridlocked. Descending is equally intense. Brake management is critical. Overheat them on the long downhill curves, and stopping becomes increasingly difficult. Visibility can drop suddenly due to fog or snowfall. A hairpin that seemed manageable minutes ago becomes a slippery trap. Los Caracoles is not a road you cruise casually. It demands rhythm, precision, mechanical awareness, and every turn reminds you that gravity is always waiting. E6 Highway, North Cape, Norway. The E6 Highway is Norway's main artery. But as you drive further north toward the North Cape, civilization begins to thin and nature takes over. This is Arctic territory. The road stretches through vast, exposed landscapes where wind has no obstacles. During winter, snowstorms create whiteout conditions so complete that road and sky merge into a single blank horizon. You lose depth perception, you lose reference points, temperatures plunge. Ice forms quickly, even when the road appears dry. Black ice hides beneath thin layers of snow, turning gentle curves into sudden slides. There are sections where the road narrows dramatically. Two large trucks approaching from opposite directions must slow carefully, mirrors inches apart, while cliffs drop toward the frigid Arctic Ocean below. Strong crosswinds are constant. They hit sideways without warning, pushing vehicles toward the edge. In winter darkness, when daylight lasts only a few hours, visibility becomes a psychological challenge. Long stretches feel isolated, remote, silent. Brake systems endure extreme stress when descending icy slopes. Engine braking becomes essential for maintaining control. If a storm intensifies, authorities sometimes close sections temporarily. Convoys may form, led by snowplows to guide drivers safely through blizzard conditions. Unlike mountain passes with dramatic hairpins, the E6's danger lies in exposure. Open land, open sea, open sky, no protection from the elements. Driving toward North Cape feels like approaching the edge of the continent itself. And up here, the Arctic decides who passes safely. Karnali Highway, Nepal. There are roads built with engineering, and then there are roads carved by necessity. The Karnali Highway in western Nepal connects some of the most remote districts in the country. It stretches through rugged Himalayan terrain where mountains don't gently slope. They collapse downward in violent, unstable cliffs. Much of this highway is narrow, unpaved, and cut directly into vertical rock faces. On one side, raw mountain wall. On the other, a drop that disappears into deep river gorges below. Guardrails are rare. During monsoon season, the road transforms into mud. Entire sections become soft, unstable, and unpredictable. Landslides are common. Rocks fall without warning. Sometimes the road itself simply gives way. Vehicles inch forward carefully, tires slipping on loose gravel. When two buses meet on a narrow stretch, one must reverse, sometimes for hundreds of meters, until a slightly wider patch appears. Imagine reversing on a cliff edge with no barrier. Dust clouds reduce visibility in dry months. In rainy months, wheels sink into thick sludge. Engines struggle. Brakes wear down rapidly during steep descents. For many communities along this highway, it is the only supply route for food, medicine, and fuel. That means overloaded trucks frequently travel these unstable paths. One mechanical failure, one tire burst. One misjudged edge. There is no recovery zone. The Karnali Highway isn't just a dangerous road. It is survival carved into stone. Route 500, Newfoundland and Labrador, Canada on a map, it looks harmless. Route 500 in Newfoundland and Labrador stretches through vast forests and isolated terrain. It's long, remote, and deceptively calm, but remoteness creates its own kind of danger. This highway cuts through wildlife territory. Moose collisions here are not rare incidents, they are a serious threat. Adult moose can weigh over 500 kilograms, and their height means impact often shatters windshields directly at driver level. Now imagine driving at night. Street lighting is minimal across long stretches. Fog rolls in from coastal areas. In winter, snowstorms arrive suddenly. Black ice forms silently across the asphalt. There are sections where fuel stations are dozens of kilometers apart. Cellular service drops without warning. If a vehicle breaks down in freezing temperatures, help may not come quickly. Temperatures can plunge far below zero. Engines struggle to start. Batteries fail. Tires harden in extreme cold, reducing grip. And then there is monotony. Long, straight stretches through dense forest can lull drivers into a false sense of security. Fatigue builds quietly. Reaction time slows. Suddenly, headlights reflect off two towering legs in the darkness. At highway speed, there is almost no time to respond. Route 500 is not dramatic. It doesn't hang off cliffs or twist through mountain passes. Its danger hides in silence, isolation, wildlife, weather, and the realization that in some places you are very, very alone. Danakil Desert, Ethiopia. If you want to understand what the surface of another planet might look like, you don't need a spacecraft. You need a four-wheel drive vehicle, an experienced guide, exceptional heat tolerance, and the willingness to travel to one of the most inhospitable places on Earth. The Danakil Depression in northeastern Ethiopia is not just the hottest permanently inhabited place on the planet. It is a geological and chemical spectacle that looks, sounds, and smells unlike anything else in the known world. The Danakil Depression sits at the convergence of three tectonic plates, the Nubian, Somali, and Arabian plates, that are literally tearing apart from each other in a process called rifting. The ground here is moving. The Earth's crust in the depression is among the thinnest anywhere on the continental surface, and the magma below is extraordinarily close. Surface temperatures regularly exceed 50 degrees Celsius, that is over 120 degrees Fahrenheit, making it one of the few places on Earth where average annual temperatures exceed the livable threshold for most organisms. And yet, humans have lived here for centuries. The Afar people, nomadic pastoralists of extraordinary resilience, have called this furnace home since antiquity. What draws visitors and scientists to the Danakil despite its extremity is the visual spectacle created by its unique geochemistry. The Dalol volcanic crater complex, at the northern end of the depression, contains what may be the most alien-looking landscape on the planet's surface. Neon green and yellow acid pools, brilliant orange hydrothermal springs, bright red iron oxide formations, and networks of white salt crystals in every direction. The colors are produced by sulfur, iron, silica, and chloride compounds reacting with the superheated brine that bubbles up from the hydrothermal vents below. The temperature of this brine at some vents exceeds 100 degrees Celsius. The pH of the most acidic pools approaches more corrosive than battery acid. Remarkably, life exists here. Microorganisms called extremophiles, specifically archaea and certain bacteria, have been discovered thriving in the Dalol acid pools. Their existence in such conditions has profound implications for the search for extraterrestrial life. If biology can survive here, the range of environments across the universe where life might exist is dramatically wider than previously assumed. Beyond Dalol, the Danakil contains vast salt flats, the remnants of ancient seas that evaporated millions of years ago, some of them over 400 feet thick. The Afar salt miners who work these flats do so exactly as their ancestors did centuries ago, cutting rectangular slabs of rock salt by hand using traditional tools, loading them onto camel caravans, and walking them out of the depression to market. It is one of the last places on Earth where this ancient salt trade still operates. At night, the active lava lake of Erta Ale, a nearby shield volcano, glows orange against the black sky, its reflection visible across the salt flats for miles. The Danakil Depression is our planet's most extreme landscape, its most chemical, its most geologically raw. It is beautiful in the way that only truly dangerous things can be. Paso de los Libertadores, Chile, Argentina. High in the Andes, near the border of Chile and Argentina, lies one of South America's most critical mountain crossings. Paso de los Libertadores is a lifeline for trade between the two countries, but it demands respect from every driver who attempts it. The road climbs steeply through dramatic elevation changes. Hairpin turns stack upon each other as vehicles ascend toward the Cristo Redentor tunnel near the summit. Altitude affects engines, power drops, braking distances increase during descents. Winter transforms the pass completely. Heavy snowfall blankets the roadway. Ice forms beneath compacted snow. Visibility can collapse within minutes as Andean storms roll in. Massive freight trucks dominate this route. Long convoys crawl upward in low gears. On sharp bends, trailers swing wide, leaving little margin for error. Guardrails exist, but the drop beyond them is immense. Descending requires discipline. Overheated brakes can lead to catastrophic failure. Runaway truck ramps are placed strategically, a silent reminder of what has happened here before. Traffic congestion can trap vehicles for hours if weather conditions deteriorate. When authorities close the pass due to snow, lines of trucks stretch for kilometers on both sides of the border. This isn't a scenic mountain drive. It's a test of patience, mechanics, and nerve. Every turn feels deliberate, every shift of gear calculated. Because at this altitude, mistakes travel faster than help. Shinkansen, Japan, it is the train that changed the world. The Shinkansen, or bullet train, is not just a mode of transport. It is the symbol of Japan's post-war recovery and technological prowess. Launched in 1964, just in time for the Tokyo Olympics, the first line connected Tokyo and Osaka. It was the world's first high-speed rail system. Today, the network spans the entire country, with trains reaching operational speeds of 200 mph, 320 km/h. But speed isn't the only marvel, it's the safety and punctuality. The Shinkansen has carried over 10 billion passengers with 0 passenger fatalities due to derailments or collisions. This is achieved through a dedicated track system. No slower commuter or freight trains share the rails. The tracks are welded continuously to reduce vibration and noise. The trains are aerodynamic masterpieces, with long duckbill noses designed to prevent sonic booms when entering tunnels. This tunnel boom problem was solved by an engineer who was inspired by the beak of a kingfisher diving into water without splashing. The punctuality is legendary. The average delay is measured in seconds, usually less than a minute per year. If a train is late, it makes national news. The system is also earthquake-proof. When seismometers detect the primary waves of an earthquake, the power is cut, and emergency brakes engage automatically, stopping the train before the more destructive secondary waves hit. It is a system that thinks faster than disaster. Riding the Shinkansen is like gliding on air. It transformed Japanese society, enabling people to live hundreds of miles from where they work. It set the gold standard for rail travel globally, inspiring the TGV in France and high-speed networks in China. It is a blue and white streak cutting through the rice paddies and cities, a relentless machine of efficiency and grace. The door to hell, Turkmenistan. In the middle of the Karakum Desert in Turkmenistan, one of the world's most remote and least visited countries, a crater burns. It has been burning continuously since 1971. Its flames are visible from 40 kilometers away. At night, its orange glow reflects off the desert sand and the few clouds that pass overhead, creating a dome of light in the darkness that is visible, according to locals, from the windows of aircraft at cruising altitude. Travelers who encounter it for the first time consistently use the same word, hell. The Darvaza Gas Crater was not created by nature. It was created by human error, and then compounded by a decision that seemed logical at the time, but turned out to be one of the most dramatic miscalculations in the history of resource extraction. In 1971, Soviet geological engineers were drilling for natural gas in the desert when the ground beneath their drilling platform collapsed, creating a sinkhole approximately 70 meters wide and 30 meters deep. The collapse was caused by the drilling penetrating a large natural gas cavern, which gave way under the weight of the equipment. The engineers, concerned that the escaping methane, a potent greenhouse gas, would be dangerous to nearby villages and workers, made the decision to ignite it. They estimated the gas would burn off within a few weeks, after which the crater could be safely examined and the site rehabilitated. It is still burning. The crater has been on fire continuously for over 5 decades. The gas field beneath Darvaza is enormous. Far from exhausting itself within weeks, the methane reservoir has continued to feed the fire with no detectable reduction in intensity. The flames reach heights of up to 15 meters at the crater's edge. The heat at the rim is intense enough to make extended close-up observation uncomfortable. The smell of burning gas and sulfur permeates the air for miles downwind. At night, when the desert is cold and dark and completely silent, the crater is a genuinely otherworldly sight, a glowing, roaring pit of orange and yellow fire in the dead center of an ancient, featureless desert. The Turkmenistan government has made several announcements over the decades about extinguishing the crater, most recently issuing orders to do so in 2022. As of the latest reports, the crater continues to burn. Adventurous travelers make the long desert journey to camp beside the crater specifically for the nighttime experience, sitting in the cold desert air, close enough to feel the warmth, watching the fire move and shift. It is hypnotic, disturbing, and genuinely unlike any other experience the planet offers. A fire lit by accident that refused to stop. A reminder that the Earth contains reservoirs of energy so vast they can defeat human attempts to exhaust them. The door to hell is a mistake that became a monument, and it burns on. The name Deception Pass comes from an 18th century navigation era. Captain George Vancouver, surveying the Pacific Northwest coast in 1792, initially believed that Fidalgo Island was connected to the mainland and bypassed the narrow strait. When he later returned and found it was in fact a pass between islands, he named it for the deception it had presented. The geological features that created the confusion, the narrowness of the strait, the surrounding vegetation. The way the rock formations close around the water are the same features that make the bridge crossing of this pass one of the most dramatic short bridge experiences anywhere in the American West. The Deception Pass Bridge, completed in 1935, consists of 2 spans connecting 3 landmasses: Fidalgo Island, Pass Island, and Whidbey Island. The northern span crosses the main channel of Deception Pass at a height of approximately 180 feet above the water, a body of water that is not merely picturesque, but actively dangerous to navigation. The tidal currents through the narrow strait can exceed 8 knots, creating whirlpools, standing waves, and hydraulic features that have claimed boats and, historically, lives. The water in the pass appears to be in constant, agitated motion, a visible reminder that what lies below the bridge is not still water, but a marine system under significant continuous pressure. The bridge's steel arch structure carries 2 lanes of Washington State Highway 20 between the islands, with a pedestrian walkway adjacent to the traffic lanes. Walking the pedestrian path, looking down from 180 feet onto the turbulent water in the pass, watching the tidal current move against the rock walls of the narrow channel, hearing the Pacific wind come through the strait from the west, is an experience of genuine physical immediacy. The steel vibrates, not alarmingly, not in any way that suggests structural concern, but in the way that all large steel structures vibrate when wind and traffic loads are applied simultaneously. The vibration comes through your feet and your hands and establishes, continuously, the fact that you are not on solid ground. You are on a structure in motion, above water in motion, in a marine environment that was moving long before the bridge arrived and will continue moving long after it is gone. The bridge was built in only a few months, opening on July 31, 1935, at a cost of approximately $482,000, a remarkable pace and economy even by Depression-era standards. The speed of construction reflected both the engineering confidence of the era's bridge builders and the practical pressure to connect Whidbey Island to the mainland, in a way that the ferry system had long failed to achieve reliably. 80 years later, the bridge still stands, still carries the highway, and still provides the same experience of vertical exposure above fast water that it offered to the first pedestrians who crossed it in the summer of 1935. Ice Volcano National Park, Kazakhstan. In winter, in the vast and frozen steppe of southeastern Kazakhstan, something rises from the ground that should not exist. A cone of ice, perfectly formed, up to 40 feet tall, with a crater at its summit from which warm water flows and mist drifts upward into the freezing air. It looks like a volcano. It behaves like a volcano. It glows in the winter sunlight like a lantern of translucent blue ice. But it is not built by heat. It is built by cold. The ice volcano of Altınoluk National Park, located in the foothills of the Dzungarian Alatau mountain range east of Almaty, is one of the rarest natural formations on Earth. The phenomenon begins deep underground, where natural mineral springs are fed by snowmelt filtering through the mountain rock above. This water, pressurized by the overlying geology, is forced upward through narrow fissures in the ground and emerges at the surface as a flowing spring. In summer, the spring simply flows across the ground, unremarkable, unnoticed. But as winter arrives and temperatures in the Kazakh steppe plunge to -20 and -30 degrees Celsius, the emerging water freezes almost the instant it hits the air. And here is the extraordinary part: the freezing is not random. The water builds up around the exit point of the spring in concentric layers, each outflow freezing over the last, adding height and mass with every passing day. The cone grows from the outside in, thickening layer by layer like a stalactite building in reverse, not downward, but upward and outward. As the outer layers freeze and seal, the pressure of the water beneath builds further, eventually forcing the water up through the center of the cone and out through the crater at the top, where it spills over the edge and adds another layer of ice. The result is a perfectly conical ice structure with a hollow core, technically more similar to a geyser cone than a true volcanic cone, but visually indistinguishable from a miniature volcano, complete with a steaming crater and flowing lava of water. When sunlight hits the structure, the ice reveals its interior, trapped bubbles, pale blue layers, the faint tracery of the water channels that built it. It glows from within like a paper lantern. The cone does not persist. Each spring, as temperatures rise, it melts back to nothing, leaving only the wet ground of the spring behind. Each autumn, as cold returns, it begins again. The same spring, the same process, the same impossible structure rebuilding itself in the same location, year after year, as reliably as the seasons themselves. Visiting the ice volcano requires a significant journey. Altinamel is remote even by Kazakh standards, and winter travel in the steppe demands serious preparation. But those who make the effort find something genuinely unique, a natural formation found in only a handful of locations worldwide, perfectly formed, perfectly temporary, and perfectly beautiful. Underwater waterfall, Mauritius. From the deck of a boat off the southwestern coast of Mauritius, you can look down through crystal clear water and watch what appears to be a waterfall cascading into an abyss thousands of feet below the ocean surface. The water seems to spiral downward in sheets, like a river finding a cliff edge and tumbling off into darkness. It is one of the most extraordinary visual phenomena in the ocean, and it is entirely an illusion. No water is actually falling at Mauritius. The underwater waterfall is a breathtaking optical trick created by the interaction of ocean currents, sand, and submarine topography. Just off the southwestern coast, near the village of Le Morne, Brabant, the ocean floor drops suddenly and dramatically, a continental shelf edge that plunges from shallow tropical reef depth to over 4,000 feet within a remarkably short horizontal distance. The surrounding seabed, particularly the shallow lagoon areas behind the barrier reef, is covered in fine white sand and dark silt. When tidal currents and wind-driven surface flows move across this shelf edge, they sweep the sand and silt from the shallow areas and carry them over the edge. The material flows downward along the steep submarine slope in dense, swirling cascades, exactly like a river running over a waterfall, except that the water, in this case, is sand, silt, and ocean water moving together through the deeper, clear ocean below. The contrast in color, the white sand and dark silt spiraling through the transparent turquoise water against the deep blue of the abyss, creates an effect so convincing that even experienced marine professionals sometimes double-check the footage. From the air, typically from a helicopter or light aircraft, the effect is even more dramatic. The turquoise shallow water of the Mauritius lagoon appears to funnel directly into a darker, swirling vortex, as if the entire ocean is draining through an invisible plug hole. Aerial photographers and drone operators have made this shot one of the most shared oceanic images in the world, a visual that consistently generates disbelief and demands for explanation when encountered without context. Divers and snorkelers who explore the area near the shelf edge can experience the phenomenon from below, feeling the subtle but real current caused by the sand displacement, watching the sediment stream past and downward. The sensation is surreal, standing at the edge of a submarine cliff, watching material cascade past you into darkness far below, with no fixed reference point to anchor your orientation. For a moment, it genuinely feels like standing at the edge of a waterfall, except the sky above you is made of water, and you are already inside the ocean. The illusion depends on specific light conditions, best observed from above during morning or midday light, when the sun angle illuminates the contrast between shallow and deep water most dramatically. It cannot be seen from the shore and is difficult to photograph from sea level. But from above, in the right light, it is one of the most jaw-dropping sights the ocean has ever produced. Blue Fire Volcano. Indonesia. There is a volcano in East Java that burns blue. Not the familiar orange and red of conventional fire, not the yellow of burning sulfur in daylight, but a cold, electric, vivid blue that crawls across the crater floor like neon light pools in cracks and crevices, and flows in slow rivers down the inner slopes of the crater wall. It is one of the rarest fire phenomena on Earth, and it is as beautiful as it is dangerous. Kawah Ijen, the White Crater, sits at 2,799 meters above sea level in the Ijen volcanic complex of East Java, Indonesia. The mountain is part of an active volcanic chain, and its summit crater contains one of the most acidic lakes in the world, a turquoise-green body of water so chemically aggressive that its pH level approaches 0. The lake is approximately 200 meters wide and over 60 meters deep, and its surface temperature ranges between 85 and 170 degrees Celsius. Into this lake drain the hydrothermal vents that line the inner crater walls, vents that emit a continuous stream of high-temperature volcanic gases, primarily sulfur dioxide and hydrogen sulfide. It is these gases that create the blue fire. As the sulfuric gases emerge from the vents at temperatures exceeding 600 degrees Celsius, they immediately combust on contact with the oxygen in the surrounding air. Normal sulfur burns yellow-orange. But at these extreme temperatures, and at the density at which the gases emerge from Eigen's vents, the combustion produces blue and violet flames that can reach up to 5 meters in height. The effect is most dramatic at night, when the ambient light is low enough for the blue luminosity to dominate, transforming the crater into an otherworldly spectacle of electric blue rivers flowing across a darkened volcanic landscape. Visiting Eigen to witness the blue fire requires a significant commitment. The trek to the crater rim begins at 1 a.m. to ensure arrival before dawn. The blue fire is visible in the darkness, but begins to disappear in the diffuse light of pre-dawn. The path is steep, the air is cold at altitude, and the last section to the rim is on loose volcanic gravel. From the rim, guides lead those who choose to descend into the crater itself, a demanding scramble down steep, unstable slopes into a valley thick with sulfuric gas. Respiratory protection is essential. Even with masks, the concentration of hydrogen sulfide near the vents can be overwhelming. Here, in this toxic, beautiful inferno, work the sulfur miners of Kawa Eigen, men who descend into the crater every night and every morning to harvest yellow sulfur that crystallizes at the vent openings. Breaking it free with iron bars and loading it into rattan baskets that they carry out on their shoulders. Each load weighs between 70 and 100 kilograms. Each man makes this journey 2 to 3 times per day. They earn roughly $1 per kilogram, among the hardest earned wages anywhere on the planet. The blue fire of Kawa Eigen is beautiful. The men who work beside it are extraordinary. Eiffel Tower, France. When it was built for the 1889 World's Fair, Parisians hated it. They called it a useless monstrosity and a hollow candlestick. Today, the Eiffel Tower is the most visited paid monument in the world and the universal symbol of romance and Paris itself. Standing 1,083 feet tall, it was the tallest man-made structure in the world for 41 years until the Chrysler Building overtook it. Designed by Gustave Eiffel's firm, it was a radical display of what iron could do. The tower is assembled from 18,038 pieces of puddle iron held together by 2.5 million rivets. The design is pure mathematics. The curvature of the legs is calculated to offer the most efficient wind resistance. Despite its open lattice look, the tower is incredibly strong yet light. If you melted down all the metal, it would fill a block only about 6 centimeters deep across the tower's base. The 4 legs align perfectly with the compass points. Construction was a spectacle of precision. The rivet holes were pre-drilled to within 1/10 of a millimeter. The tower was supposed to be dismantled after 20 years. It was saved only because it proved useful as a radio antenna tower. In WWI, it jammed German radio communications, helping to save Paris. Today, it sparkles every night with thousands of strobe lights, a light show that was meant to be temporary for the year 2000, but was kept by popular demand. It grows about 6 inches in the summer due to thermal expansion of the iron. The Eiffel Tower is the Iron Lady of France. It proves that utility and art can merge. What started as a temporary exhibit became the permanent soul of a city. It stands as a reminder that great ideas are often misunderstood at first, but true engineering brilliance stands the test of time. Infinity Bridge, Stockton-on-Tees, UK. There is an exact viewing angle available from the southern bank of the River Tees in Stockton-on-Tees on a still, grey English morning, at which the Infinity Bridge and its reflection in the water below merge into a precise figure 8. The symbol for infinity, not a designed symbol printed somewhere, an emergent symbol created by the relationship between the engineered form above the water and the mirror surface below it. The bridge does not display its meaning, it creates its meaning. This is a different and more interesting thing. The Infinity Bridge, opened in 2009, consists of 2 steel arches of differing heights spanning the River Tees between the banks of Stockton and Thornaby. The 2 arches are offset from each other in plan, not placed symmetrically, but shifted so that their peaks do not coincide. A main cable runs from arch to arch, from which the bridge deck is suspended, creating a hybrid structural system that distributes load through both arch compression and cable tension simultaneously. The asymmetry is structural as well as visual. The taller arch carries more of the load. The visual effect of the asymmetry, the way the 2 arches appear to interact, to lean toward each other, to form a relationship that is neither symmetrical nor random, is the result of engineering logic expressed in an aesthetic language. The bridge was built as part of a broader regeneration of the Stockton-Thornaby riverside, a stretch of the Tees that had been industrial and largely inaccessible to pedestrians for much of its post-war history. The Infinity Bridge was the centerpiece of a public realm investment intended to transform the riverbanks into spaces for walking, gathering, and civic life. It succeeded. The bridge became immediately popular, not only as a crossing, but as a destination. People walked to the Infinity Bridge specifically to see it, to photograph it, to stand on it and look at the river and the 2 arches converging above them. At night, integrated LED lighting traces the full outline of both arches, reflects in the river below, and creates a light installation that changes color seasonally. The reflection doubles the visual impact. 2 arches become 4, the water becomes a second sky, and the infinity symbol that appears by daylight becomes, by night, a glowing loop of light above and below the water simultaneously. The bridge was not designed to be a light installation. It was designed to be a bridge, but in the hands of its designers, Expedition Engineering and Spence Associates, every design decision was made with the understanding that a bridge is not just a way to cross water. It is a way to occupy space beside water and to make that occupation worth the journey. Beneath the jungle floor of Mexico's Yucatan Peninsula, an extraordinary geological secret hides in plain sight. Thousands of sinkholes, called cenotes, puncture the limestone surface of the peninsula, opening into an underground world of caves, passages, and chambers that stretches for hundreds of miles in the largest cave system ever mapped. And in one of those cenotes, divers descend through clear freshwater and then pass through what appears to be the surface of a river flowing far beneath the sea. Cenote Angelita, Little Angel, sits near the town of Tulum on Yucatan's Caribbean coast. From the surface, it appears unremarkable, a circular pool of clear blue water, perhaps 60 feet across, surrounded by trees in a jungle clearing. The entrance is narrow and the descent begins immediately. The water is extraordinarily clear, visibility extending to 30 meters or more, and the walls of the cenote are covered in the roots of jungle trees that have grown downward through the limestone in search of water. As divers descend past 100 feet, the temperature drops and the limestone walls close in slightly. And then, at approximately 115 feet, something impossible appears below, a river, not a metaphor, not a visual trick. A river with banks, a surface, a gentle current, and even submerged trees lining its banks, flowing silently in the darkness beneath the freshwater layer above. What divers are seeing is a halocline, a sharp boundary layer between 2 bodies of water of dramatically different salinity. The Yucatan Peninsula is underlain by a vast lens of freshwater, rain, that that has filtered down through the porous limestone over thousands of years. But beneath this freshwater lens lies saltwater, oceanic water that has permeated the rock from the sea. Because saltwater is significantly denser than freshwater, the two layers do not mix. They sit one above the other, separated by a boundary that is often no more than a few centimeters thick. At the halocline surface, the optical properties of the two water types, their different refractive indices, create a visible, shimmering boundary. Looking across it horizontally, the boundary appears as a dense, mirror-like surface. Looking through it, objects on the other side appear distorted, blurred, wavering, as if seen through frosted glass. The effect from above is precisely the appearance of a river, a surface with reflections, with apparent current from the light refraction, with submerged features visible but distorted below. The trees visible beneath the halocline in Angelita are the trunks and branches of ancient forest that once grew here when the cave system was dry, thousands of years ago, before sea levels rose and the saltwater intruded. They are perfectly preserved by the anoxic high salinity conditions below the halocline, ancient wood in an ancient sea, sealed beneath a freshwater sky. Museum of the Future, UAE. In the heart of Dubai, a city known for piercing the clouds with glass needles, sits a structure that defies all logic. The Museum of the Future is not a skyscraper. It is a gleaming silver torus, a giant eye looking toward tomorrow. Standing 253 feet tall, this architectural masterpiece has no corners, no columns, and seemingly no beginning or end. It is often described as the most beautiful building on Earth, a title it earns through its sheer audacity and elegance. The void in its center represents the unknown, the future we have yet to write, while the solid structure represents the knowledge we possess today. The engineering behind this pillarless wonder is nothing short of miraculous. The building's shell is a diagrid framework made of 2,400 diagonally intersecting steel members. This skeleton supports the entire weight of the structure without a single internal column, creating a seamless, open interior space. The facade is a jigsaw puzzle of 1,024 stainless steel panels, each one unique, manufactured using robotic arms usually reserved for the aviation industry. Covering these panels is Arabic calligraphy, actually serving as the building's windows. The script, written by the ruler of Dubai, quotes hopes for the future, glowing with LED light at night to turn the building into a poetic beacon. Inside, the museum is not a repository of the past, but a gateway to the year 2071. Visitors board a simulated spacecraft, the Hope probe, to dock with a space station orbiting Earth. It is an immersive theater of possibilities, exploring bioengineering, ecosystem regeneration, and space travel. The exhibits challenge you to think about climate change, spirituality, and technology not as threats, but as tools for survival. Unlike traditional museums where you look at artifacts behind glass, here you are the artifact. Your interaction drives the narrative. Sustainability is woven into its DNA. The building is powered by a dedicated solar park, generating 4,000 megawatts annually, and it features greywater recycling and passive solar architecture. It achieved LEED Platinum status, the highest rating for green buildings. This isn't just a tourist attraction, it is an incubator for global innovation, bringing together great minds to solve humanity's toughest challenges. The Museum of the Future stands as a permanent reminder that the future isn't something we await. It is something we design, build, and inhabit today. Meteor Crater, Arizona, United States. 50,000 years ago, a piece of space rock traveling at roughly 26,000 miles per hour entered Earth's atmosphere above what is now the northern Arizona desert. It was approximately 160 feet in diameter and composed almost entirely of iron-nickel metal, a dense, heavy, almost inconceivably tough object that punched through the atmosphere in seconds and struck the desert floor before any living creature within range had time to react. The explosion was equivalent to approximately 10 megatons of TNT, 600 times more powerful than the atomic bomb dropped on Hiroshima. It vaporized the meteorite itself almost completely. And it left behind a hole in the desert that we still visit today, still perfectly preserved, still almost exactly as the impact left it. Barring a meteor crater, also known as Meteor Crater, or scientifically as the Canyon Diablo Crater, is the best preserved meteorite impact crater on Earth. It measures approximately 3,900 feet across and 570 feet deep, with a raised rim that stands 150 feet above the surrounding desert floor. The crater is large enough to contain a full-size sports stadium on its floor with room to spare, looking down from the rim into the bowl below. The sense of scale is initially deceptive. The crater appears almost manageable until you spot the small model astronaut placed on the opposite rim by the visitor center, barely visible as a dot, and realize just how enormous the depression actually is. The crater's extraordinary preservation is due entirely to the extreme aridity of the Arizona desert. In wetter climates, erosion from rain, ice, and vegetation would have softened and degraded the crater's sharp features over thousands of years. Here, the rainfall is so low, typically under 8 inches per year, and the temperatures so extreme that the rock has barely changed since the moment of impact. The rim, the walls, and the floor of the crater remain crisp, geometrically precise, and geologically immediate, as if the impact happened within living memory rather than 50 millennia ago. The crater played a crucial role in the development of planetary science. When it was first studied seriously in the early 20th century, the prevailing scientific opinion held that all craters, including those on the Moon, were volcanic in origin. Barring a crater was the site where that consensus was overturned. The discovery of mineral forms, shocked quartz and coesite, that can only be produced by the extreme pressures of an instantaneous impact, provided irrefutable evidence that craters could be created by collisions, not just by volcanic activity. This discovery revolutionized our understanding of the Moon's surface, the history of Mars, and the role of impacts in shaping all planetary bodies in the solar system. Small fragments of the Canyon Diablo meteorite, the one that created this crater, are still found scattered across the surrounding desert. You can hold a piece of the meteorite in the visitor center, cold, impossibly dense, dark iron gray, older than the Earth itself. Space, crystallized and placed in your hand. The crater it left is a permanent reminder that the universe has always reached down to touch our world, and that sometimes that touch is violent beyond imagination. 3 bridges cross the Yangpu River in the area of Yangpu District in Shanghai's north. The Yangpu Bridge, the third of these to be completed, is the oldest cable-stayed bridge of the 3, and the one that arrives at its visual impact through scale rather than subtlety. Towers 223 meters tall, a main cable span of 602 meters. Red-painted concrete surfaces that at certain times of day and in certain light conditions produce a color temperature that sits uncomfortably between industrial and monumental. The Yangpu Bridge does not defer to its surroundings. It asserts itself. The Yangpu River at the Yangpu crossing is subject to currents that shift with tidal cycles in the Yangtze estuary downstream, creating flow patterns that change direction multiple times per day and generate complex hydraulic conditions at the bridge piers. Large vessels navigating this section must coordinate their movements with the current direction to maintain steerage. An error in timing a transit here is not merely inconvenient, but potentially dangerous in a river with traffic densities that make collision risk real. The bridge towers stand in this environment, their foundations anchored into the riverbanks rather than the active channel, but the hydrodynamic forces on the approach structures are present and continuously monitored. The hollow visual effect that drivers on the Yangpu Bridge report, the sense that the perspective alignment of the approach slope and the bridge deck creates ambiguity about real distance, is a documented navigation concern. The approach ramp from Yangpu district rises to bridge deck height in a curve that, at certain approach speeds, makes the connection between ramp and deck appear to occur later than it does. The consequence, vehicles entering the bridge deck at a speed and angle calibrated for the ramp rather than the deck, is a specific, recurring cause of the control incidents that the Yangpu Bridge records at higher frequency than its more recently designed peers. The bridge has appeared in multiple Chinese films depicting collapse scenarios, a choice by filmmakers that reflects the bridge's visual dominance and the specific aesthetic of its towers, which frame open space in a way that photographic composition treats as inherently dramatic. There is a particular angle, approaching from the north, at which the two towers align with the river and the sky in a way that film directors and photographers have exploited consistently. Red concrete against grey water, the cable geometry creating a fan pattern above the roadway. The river below suggesting depth and movement, and the fundamental indifference of flowing water to what humans have chosen to build above it. Greenland, there is a sound that precedes the carving. A deep, resonant crack, more felt in the chest than heard with the ears, that splits the silence of the Arctic like a rifle shot, amplified to the scale of a mountain. It is the sound of ice under unimaginable stress, reaching its breaking point. It is the last sound a glacier makes before releasing a piece of itself to the sea. And at Ilulissat Icefjord in western Greenland, this sound rings out almost every single day. The Ilulissat Icefjord, Surmek Kugelek in Greenlandic, is the most productive glacier in the northern hemisphere and one of the fastest-moving glaciers in the world. The glacier moves forward at an average rate of 20 to 46 meters per day, up to 40 meters per day in peak periods, driven by the extraordinary accumulation of snow in Greenland's interior, which compresses under its own weight into ice and flows inevitably downhill and seaward. As the glacier's terminus reaches the fjord, where the water is deep enough to float the ice, enormous sections break free and drop into the sea with an explosive force that sends shockwaves through the water for miles. The icebergs produced by Ilulissat Icefjord are enormous. Some rise over 100 meters above the waterline, and since approximately 90% of an iceberg's mass is below the surface, that means the full depth of these structures can exceed 1,000 meters. They are larger than city blocks. Some are larger than city districts. In certain seasons, the fjord becomes so choked with freshly carved icebergs that the water itself is barely visible. The surface appears as a fractured white-blue cityscape of ice towers, arches, and ridges stretching to the horizon. These icebergs drift out of the fjord and into the Labrador Sea, where they join a southward current that carries them gradually toward the North Atlantic shipping lanes. The iceberg that sank the RMS Titanic in 1912, most likely carved from the Ilulissat Glacier, drifted southward for months and made its fatal encounter with the great ocean liner approximately 1,600 kilometers south of the Icefjord. The ice of Ilulissat, magnificent and ancient, has shaped human history in ways its frozen silence could never express. The Icefjord was designated a UNESCO World Heritage Site in 2004 in recognition of its geological significance and its role in climate science. The rate of ice carving here has accelerated dramatically in recent decades, a direct and measurable consequence of rising Arctic temperatures. Scientists studying Ilulissat are not simply watching a natural spectacle. They are reading a warning written in ice about the future of the planet's oceans. To stand on the viewing platform above the fjord and watch an iceberg carve, to feel that crack through your feet, watch the ice fall, and see the wave radiate outward across the dark water, is to witness something ancient and urgent simultaneously. Beauty and alarm frozen together. The combination of a public road bridge and a large-scale amusement ride is not a combination that appears in any conventional engineering planning document. Bridge design and fairground design operate from different structural premises, different safety philosophies, and different assumptions about the relationship between the humans using the structure and the forces applied to it. The Yongchuan Bridge in Chongqing, China, has combined them anyway. A Ferris wheel with a diameter of approximately 88 meters, nearly 290 feet, is attached directly to the Yongchuan Bridge, mounted on the bridge structure itself, its base integrated into the bridge deck. Its rotating mass, turning continuously above the river traffic on one side and the road traffic on the other. The wheel weighs approximately 900 tons. The bridge structure beneath it was not originally designed to carry a 900-ton rotating load. It was designed to carry road traffic. The structural reinforcement required to accommodate the Ferris wheel to transmit its vertical and dynamic loads into the bridge's foundation system without inducing unacceptable deformation or vibration required engineering solutions that had no direct precedent. The dynamic loads are the critical issue. A Ferris wheel that is turning is not simply a 900-ton mass. It is a 900-ton mass whose center of gravity is continuously shifting as the gondolas rotate around the central axis. This shifting creates oscillating forces, not just vertical, but lateral and rotational, that are transmitted directly into the bridge structure at every point of contact. The bridge, meanwhile, is carrying its own dynamic loads from vehicle traffic, thermal expansion and contraction, and whatever the Jialing River is doing to its foundations at any given moment. The interaction between all of these load systems is complex in a way that requires continuous monitoring. In 2015, a power outage left Ferris wheel passengers suspended above the bridge for nearly 40 minutes before backup systems restored the wheel's movement capability. The incident required emergency response coordination across two overlapping infrastructure systems, the bridge's management authority and the amusement ride operator, in a scenario that neither had fully anticipated. The response was adequate. The passengers were unharmed. But the incident crystallized the specific category of risk that the Yongchuan combination creates: the normal risks of a bridge, plus the normal risks of a fairground ride, plus the emergent risks that arise when the two systems occupy the same structure and must be managed as a single entity. Great Blue Hole, Belize. From an aircraft at altitude above the Lighthouse Reef Atoll off the coast of Belize, the ocean surface reveals a perfect circle of deep blue, darker, deeper, more intensely colored than the surrounding turquoise shallows. The circle is almost geometrically exact. It measures over 300 meters across. It plunges more than 120 meters straight down into darkness. It is one of the most visually striking features of the world's oceans and one of the most scientifically significant. This is the Great Blue Hole. The Great Blue Hole is a submarine sinkhole, a drowned cave system that collapsed and flooded when sea levels rose at the end of the last ice age, approximately 14,000 years ago. The geology beneath it was formed over hundreds of thousands of years, when this area was above sea level and rain percolated through porous limestone, dissolving channels, chambers, and tunnels in the rock. Over time, the roof of the largest cave system collapsed inward, leaving the circular depression that now fills with seawater. The walls of the hole descend nearly vertically for over 40 meters, at which point overhanging ledges mark the rooflines of the ancient cave system below. It is beneath these ledges that the Great Blue Hole reveals its most extraordinary feature. At depths between 40 and 70 meters, enormous stalactites, some measuring over 12 meters in length, hang from the ceiling of the ancient cave, pointing downward at precise angles. These stalactites could only have formed in dry air. Calcium carbonate cannot crystallize in water. Their presence here, submerged and perfectly preserved, is direct evidence of the sea level rise that drowned the cave system thousands of years ago. The angle of some stalactites, not vertical but slightly tilted, indicates that the cave system partially shifted or the land subsided after the stalactites had already formed. The hole was brought to global attention by Jacques Cousteau, who visited in 1971 and declared it one of the top 5 scuba diving sites in the world. In 2018, a scientific expedition led by Richard Branson and Fabien Cousteau explored the hole's depths with submarines and discovered a thick layer of hydrogen sulfide at approximately 90 meters, a chemical boundary below which no oxygen penetrates and where the sediments on the floor preserve a detailed record of past Atlantic hurricane activity going back thousands of years. The waters around the rim of the hole teem with marine life. Caribbean reef sharks, bull sharks, midnight parrotfish, and giant groupers are all regularly encountered. The hole itself is a marine protected area within the Belize Barrier Reef Reserve System, a UNESCO World Heritage Site. From the surface, it is simply the most perfectly beautiful blue circle you have ever seen. From below, it is a cathedral,